thank you, Jesus. I appreciate that. I got the recording going now. Probably good I didn't record myself earlier. Anyhow, yes, he is the man. Okay. Oh, wait a minute. I want to put this in student view. So just a sec. Okay, here you go, student view. So announcements. Exam 3 is going to be Monday. I have not got it finished. It takes a long time to put stuff in. But anyway, I'll have it by Monday for sure. I'll have it before Monday. But anyway, and I'll try to give you guys an idea of how many questions is on there once I get it done. Anyway, it's going to be Monday. There'll be a sapling. You'll go to sapling from a link that's in Blackboard. It won't be turned on until we're going to do the exam. So you won't see anything until Monday. And you come in to collaborate just like you did today. And then I'll direct you over to Blackboard, and I'll still be in Collaborate in case you guys have a question while you're doing the exam. So it'll be pretty much the same as when we were doing it in the classroom face-to-face. There'll be multiple choice questions, 5 choices, just like the previous 2 exams. It's going to focus on Chapter 3, composition of substances and solutions, and Chapter 4, reactions and stoichiometry. Be sure you can do everything on the presentations for both of those chapters. So go back through the presentations. Be sure you can do everything on the worksheets for those chapters. Those are available. And the keys are up so you can check your answers. Maybe a few questions from sapling assignments, not very many if there are any at all. There will be a few questions from chapters 1 and 2 because these are always cumulative. And so that is the deal on Chapter 3. And if you haven't already, if you need, will we have time limit for the exam? Not really. I expect people will finish it, pretty quick. But you'll have the full period on Monday, so hour and 50 minutes. And then if you still need some time and you tell me that, we'll probably can work that out too. Okay, so should not be an issue with time. Anyhow, now the way it's going to work though is, excuse me, it will randomize the order of the questions. So while one of you would be working on, say, the first question, someone else might be working on the 7th question, and someone else might be working on the 12th question, something like that. And also the responses will be randomized. So, even if you guys are sending text messages back and forth, it's not going to make much difference. Anyhow, so let's see what Governor Pritzker is up to. Okay. Anyway, whatever. Somebody did a text. Yeah, May, what's up? Okay. How many more exams should we be expecting for the semester? At least one, besides exam 3. I don't know if there's going to be an exam 4 or not. We're getting out of time here, so I just don't know. Sorry. But there will be the final exam, so that's going to cover everything. Okay, the tasks, I think, are up to date. Let's take a look and see. How many more chapters? We're going to go all the way to the end, I think. We should be there. So we should go all the way through and including the chapter on gases. I don't remember what number that is, but we should make it all the way to gases. Okay. Let's see, is that? Yeah, I need to look here. Okay, so today is April 17th. On April 19th, you should complete the topic introduction for quantum theory. Then you should complete on April 19th. Topic introduction for periodic trends, and you should complete the topic introduction for electronic structures and periodic properties. And exam 3 is going to be on the 20th, and then the final is going to be on May 13th. Now, what I'm saying there about chapter 6, that depends on how we're doing today with things, but I think we'll be okay. If not, I can move that out a little bit more. So I think that's it. I want to go here to course materials for a second, though, and just show you again that if you're needing to review for the exam, that the presentations are here where it says lecture presentations. Click on that. Chapter 1, 2, 3, and 4, parts A and B. So you can click on those, like for instance here, and you can click there, and then it will show you the presentation from part A of chapter 4. So be sure you can do everything you see on those slides. And then the other thing I was talking about was the worksheets. So I went back to course materials again, and I'm going down to worksheets. And I'll just go to this last one here, chapter 4, part B. And well, no, that's not right. Okay. Let me fix this. Glad I did this. So if you go to chapter 4, part B, the keys should be available, but I did not do that. So now they will be. So now you'll see the key for mass stoichiometry. You'll be able to see the key for living reagent and percent yield for part 1 of that. And then the key for part 2 of that. Basically, I just took that one and chopped it up into individual keys, but it's really just one worksheet. And part 3, wait, this is taking a while. Okay, part 4 of it. And then solution stoichiometry of the key for that one. Okay, let's go back and make sure you guys can see those. So if you click on course materials and worksheets, and part B of chapter 4, yeah, I see the keys, they're all there. Oh, that last one's still not showing up. Let's figure out what's going on there. Sorry guys, this is taking a while. Yep, I think maybe I did not actually do this one. Okay. So now it works. So again, go to course materials, go to worksheets, go to part 4 of part B of chapter 4, and yeah, there's the key for solution stoichiometry. Now let's make sure the other ones are there too. So I'll go to part A of chapter 4. Yeah, you got the keys for solubility rules, you got the key for oxidation numbers. So you should be good then also for chapter 3 and chapters 1 and 2. So you can go back and do those worksheets again. Okay? So I just wanted to confirm that that was available to you guys. So now, nope, not there. So now here, I'll stop sharing. And okay, now, does anybody have a question about anything? All right, well, in that case, we'll go ahead and get back into where we were on Monday. Sorry, I need to open up the presentation so I can see where we're at. Okay, finally got it. Okay, so we stopped on slide number 24. So we stopped on this slide here. Okay. On electron configurations and orbital diagrams. So just as a little review here, these right here are the electron configurations. And then the orbital diagrams, there's different ways you could do that. You could represent the orbitals with boxes like you're seeing here, or sometimes you just draw a line for each orbital. And that's the other way of doing it. And so orbital diagrams are these guys right here. So you can see here the orbital diagrams for nitrogen through neon. And it's not that big a deal to do. The only thing you want to remember is that when you have degenerate orbitals like you have here, that you put the electrons in different orbitals as long as you can. And that's because the electrons are negatively charged. They're going to repel each other. They want to be away from each other. So the best way to do that is to put them in different orbitals. Like these are all p orbitals. And remember, with p orbitals, the magnetic quantum number is going to be -1, 0, or +1. And that is the same as if we consider a Cartesian coordinate system where you have the x-axis and the y-axis and the z-axis. You can have one orbital that is on the x-axis. You could then have another orbital that is on the y-axis. And then you could have a third orbital. Okay, how about purple? It's on the z-axis. And that gets the electrons as far away from each other as possible. But when you finally get to, say, oxygen, where you have one more electron that you have to put in there, then you're going to need to pair them up. Now, since we have an up and down arrow, what that's indicating to us is that one of those, the spin is +1/2, and the other one is -1/2. We don't know which one's up and which one's down. There's really no frame of reference, so it's impossible to say which one is which. But one is in an opposite spin to the other. Okay? Now, when you start getting to bigger atomic numbers, something bigger than neon, your electron configuration is going to get really big. No, it doesn't matter which axis goes first at all, because there is no real frame of reference. That X, Y, and Z, if you rotate it 90 degrees, then all of a sudden X is where Y was and Y is where X is, if you rotated it around the Z. And then if you flipped it back 90 degrees, you get the idea. If you keep flipping that coordinate system around in space, then one axis could become another axis, and there is no frame of reference for that. It's just that they're different. Okay, so think about them as they are different, but we don't know really which one we're specifically talking about at the time. Okay, back to the electron configurations. See, with neon, this is starting to get quite a few things here. 1s2, 2s2, 2p6. It's getting big. And we don't really want to have a really long electron configuration. It starts to become cumbersome. So that gets us into something called noble gas configurations. So that's what this next slide is about, mostly, noble gas configurations. It's also about core and valence electrons. So here we have sodium, and sodium has 11, well, it's atomic number 11, and it has 11 electrons. So we're having to put those somewhere. Now, if we wrote out the entire electron configuration, it's going to look like this here. But what we can do is take, I'll change colors here. We can take these first three orbitals, the 1s, the 2s, and the 2p, and we can see what noble gas that corresponds to, and it corresponds to neon. So we can just put neon inside of brackets. And that then is going to represent, if I go back the other direction here, it's going to represent those three orbitals. And that all those orbitals are completely full. They have 2 electrons per orbital. But we have one more electron. That next electron would go in the 3s orbital, so we're showing that over here as 3s1. We're also showing it over here as 3s1. Now, another aspect of having a noble gas electron configuration is that all of the electrons that are in the noble gas part over here, where we have neon in brackets, those are core electrons. Those are in the inside of the atom. But on the outside, the outer edge of the atom, is this 3s orbital, and that contains what we're going to call valence electrons, which is going to become important in the next chapter. And those valence electrons are what participates in making bonds between 2 atoms. Okay? So the electrons here in this beige color, 3s1, that is the valence electrons for sodium. So we could say that sodium has 1 valence electron. The other 10 electrons are core electrons. Now let's go to something further down the periodic table. I'm not sure how many electrons this is, and I don't really want to count them. But anyway, it's for germanium, and we can represent its core, but we need to do 2 things. These electrons here, that I'm drawing a box around, those are all either s or p orbital electrons. So those are going to correspond to the noble gas argon over here. But we have then 10 more electrons that are in the d orbital. It's on the third level. Remember, when you're figuring out level it's in, you take where you're at in the s orbital, and you'd be at the fourth level, but then you go back one, so that's why it's 3 and not 4. And you have 10 electrons in there. So you have filled up all of those d orbitals. You need to indicate that over here in the noble gas configuration. So this first part, this is the noble gas part, or it's not the valence part, we could say. So argon in brackets, 3d10. You still have 4 more electrons that you have to put somewhere. And those are going to be in the 4s and in the 4p orbitals. So those are, as it says here, those are the valence electrons this time. So now germanium has 4 valence electrons, and then all these other ones, which I don't know how many that is, but anyway, however many we have in the core, those are the core electrons. Okay, has anybody got a question about this? Okay, let's look at another slide that's on the same subject. Well, not really. Well, it is sort of. Okay, this has got the noble gas configurations in a sense, because like, let's make this big so we can see it better. Oh, I don't want to do that. I want to move this thing a little bit. Yeah, here we go. Okay, so we've got here, say, calcium. So it's saying, okay, its noble gas configuration has a 4s, but you have to also look and see what is the noble gas. Oops, sorry. This is a little bit awkward. Okay, now I can move it over. Well, I can as long as it doesn't move. There we go. So I need to go from where calcium is over to what was the noble gas just before calcium, and that would be argon. So to complete out the noble gas configuration, I would need to put argon in brackets, and then there's 2 more electrons, and those are in the 4s orbital. So this periodic table allows you to see the electron configurations, the noble gas electron configurations for everything. But remember that what you're seeing below the symbol of the element is just the valence, not the core. For the core, you got to look back and see what is the preceding noble gas. Now it gets a little more complicated, say, if I was going to do, okay, let's do strontium. So I'm going to erase all this stuff. Well, that's interesting. Why did it not erase that? Oh, wait a minute. Duh, that's part of the slide. Okay, so now let's go to strontium. And it's right here. I think I might need to move this over. Yeah, there we go. Okay, so it's saying that, okay, it's got a 5s2. Oh, wait a minute. That's not a good example. Sorry, guys. Let's try that again. Let me find a better example than that. Okay, let's do iron, I think. Is that going to be good? No. Yeah. That'll work. Okay, let's do iron. So for iron, noble gas configuration is going to be 4s2, but then it's also going to have 3d6, and then we have to go back to its noble gas that was before it. That would be argon. And that would be its noble gas configuration. Okay? So, any question on that stuff? Okay, I want to go to the next slide and, oops, that's too big. Okay, so now here we're doing the noble gas configuration for phosphorus. And so before we do the noble gas configuration, its complete configuration would be this: 1s2, 2s2, 2p6, 3s2, 3p3. Or if we're going to do the orbital diagram, it's going to look like that. But if we want to do the noble gas configuration, we can just have its valence electrons and then go backwards in the periodic table till we get to neon. Let's go back to that previous one here, and we'll see that. No. Okay, so we're doing phosphorus here. So if I slide this over a little bit, we can see that it's got 2 electrons over here in the 3s. So it's going to be 3s2. Then when I come across to here, it's going to be 3rd level, p block, and then 3 electrons there. But then we also need then the noble gas part, so I need to go backwards a little bit. So I go from where it came into the 3rd level, and I can see that the noble gas just before that was neon, so I put neon in brackets. And so that would be its configuration, noble gas configuration. Neon in brackets, 3s2, 3p3. Just like we had here. Okay, I think I got one more. Yeah, I got. Well, we'll do a couple more slides because we're going to go to a worksheet, but I need to set it up a little bit more for you guys. So let's go a little bit further. But does anybody have a question? Okay, so go to the next slide. So we can also do, we can also do electron configurations, and we could do orbital diagrams for ions. And here's how that's going to work. If the ion is a positively charged ion, then of course we call it a cation, and we need to show what electrons were lost in order to make it positive. We take away electrons and it makes it have a positive charge. So, for example, if it's the if it is the lithium, if it's the lithium cation, before it's lithium cation, if it's just lithium, then its electron configuration is going to be 1s2 and then 2s1. But whenever it becomes the cation, we have to take away an electron. So it says the electron is lost from the highest energy level. The highest energy is 2. So we're going to take away that electron, and we're going to end up with its electron configuration looking like that, 1s2. Okay? Then if we're doing iron, we're going to jump over and do a noble gas configuration because it would be a pain to do it some other way. So if it was iron, not the cation, but just iron, then noble gas configuration is going to be argon core, or argon in brackets, and then it's going to be 3s2, 3d6. But we need to take some electrons away from the highest energy orbitals. And so in order to do that, we're going to take the one from the 3s. So those are going to go away. We're left with the 3d. So now the orbital diagram is going to look like this in order to get a 2 positive iron cation. If we need to get a 3 positive cation, then we're going to have to take 1 electron out of the 6 that are in the 3d, and so now it's going to look like this, argon in brackets 3d5. Okay, has anybody got a question on what you do if it's a positively charged ion or a cation? Okay, not hearing anything. So now we'll go to what happens if it's a negatively charged ion. So now charge is negative. That means it's got more electrons than the atom would have. And the way we do this is we add electrons so as to produce the whatever the s orbital is and whatever the p orbital is, okay, at the highest energy orbital. So if we have fluorine, then that's going to be 1s2, 2s2, 2p, 2p5. That's for just fluorine, not the ion, but just fluorine. But if we have fluoride, like we have up here with 1 negative charge, we need to add 1 electron to the 2p. So that now the electron configuration is going to look like this, 1s2, 2s2, 2p6. Now this is also the same as the electron configuration for neon. But we don't put neon in brackets and call that the configuration. Instead, we need to do it like what we're seeing over here. Okay? So don't do this. That would not be correct. Now, just when it seems like everything is pretty simple, not too bad, we got to throw in a couple more things. And that is, in chemistry, as you guys know, we try to simplify it. And then as you go on, we go back and say, well, it's not really that way. It's really a little more complicated. And then we throw in something else on top of what you heard previously. So we're going to have to do that for electron configurations. That is, sometimes the configuration is not what our system that we've been going through would give us. It's actually something a little bit different. And so those are called anomalous configurations, and we need to take a look at those. And I need to make the slide a little bit smaller. Okay, here we go. So anomalous electron configurations. The example that we're going to look at is chromium. Now this is what we would get for an electron configuration, a noble gas electron configuration for chromium. We'll say argon core, argon in brackets. Then we have 2 more electrons in the 4s orbital and 4 more electrons in the 3d orbital. And then we would say, okay, that's it. But the actual configuration is where we take 1 electron from the d orbital and we move it over to the s orbital. No, excuse me, we do it the other way around. I'm sorry. We take 1 from the s orbital and we put it over in the d orbital. So that now the d has 5 instead of 4 and the s has 1 instead of 2. The reason why that happens is what we're saying down here. Having 5 or 10 electrons in a d orbital, in other words, all the d orbitals are paired, they have a pair of electrons in all the d orbitals, or all of them are unpaired, one way or the other, that is a more stable situation. So if we can move electrons around from the s orbital to put them in the d orbital such that we get 5 or 10, it frequently will happen. So this occurs because the 4s and the 3d orbitals are very close in energy, so therefore, that's what it's showing up here, that these are pretty close to each other, therefore we can move electrons from the 3s to the d, and that's fine. Now we've got a table of the anomalous configurations that you guys need to be familiar with, and that's here. So our examples of anomalous configurations are these: copper, silver, gold, palladium, chromium, and molybdenum. So this first column here, we have what we would expect, what we would predict the electron configuration to be, and to the right is what it actually is. So in this case here, we only have 9 electrons in the d orbital. But we can take 1 electron from the s and move it into the d, and so the actual electron configuration is going to be 3d10, 4s1 instead of 3d9 and 4s2. The one right below it, for silver, is the same sort of thing. Same sort of thing here for gold. Here, for palladium, we move 2 electrons from the s orbital. And so when we come over here, there is no s orbital, just the d. So krypton core 4d10. And then for chromium, we have an example of trying to have all the orbitals with a single electron in them. So we start out here 3d4, 4s2, but if we take 1 electron from the 4s and put it in the 3d, now we have 5. Like I said before, we want to have either 5 or 10 electrons in the d orbital. And then below that is the same sort of thing here for molybdenum. We've got 4d4, 5s2, but we really want to have 4d5, 5s1. Okay? So has anybody got a question on this stuff? Because I'm going to set you up to do a worksheet here in just a second. Okay. Now, before I do that, I'm going to get rid of this, and I'm going to share my desktop because I want to show you where the worksheets are, just to make sure that everybody knows where they are. Okay, so you go back into Blackboard, course materials, scroll down some till you get the worksheet, click on that, and then click on electronic structure and periodic properties, chapter 6. And we're doing orbital diagrams and electron configurations. You click on that, and you'll get this electron configuration practice worksheet. So you guys are going to want to do that because you're not going to be able to see the one that I'm going to show you after we get started. Okay? So now I need to stop sharing my desktop, and I need to show you the orbital diagram electron configuration worksheet. Okay, let's make it big. Now, this is sort of like what you're going to have to do, but it is a little bit different because what they've done here is they didn't draw boxes. You know, you could imagine these to all be boxes, but they're not boxes. They're just lines. But they have drawn out all of the different orbitals all the way up to 3D5. Ignore a little subscript of an X and a Y and a Z. This really, I mean, it just means that these are all degenerate orbitals. So these are all at the same energy level. But you don't really need that. Oops, I think I put it in the, yeah, sorry, I did it in the wrong place. Whoops, go back. Let's get that. Well, okay. Put it here. So those X and the Y and the Z, don't worry about those. But anyway, they're giving you all the possible orbitals. You're only going to fill in the ones you need to fill in. Okay? So you're not going to be like doing all of those. Then later on, let's see, that's that page. Let's go to the next page. So you're going to be doing, okay, you're going to be doing electron configurations now instead of orbital diagrams. For chromium and magnesium, they give you the one for silicon. And then you're going to be doing noble gas configurations for chlorine, silver, and tin. They're giving you one for calcium. What they're doing here actually is they're giving you the complete configuration. Then right below that, they're showing you what the noble gas would look like. Then you're going to do orbital diagrams for some ions, sodium, calcium, and oxygen or oxide. Then you're going to do electron configurations for these ions, beryllium, lithium, and fluorine or fluoride. And then you're going to do noble gas configuration. So for 16, 17, 18, you're writing out the complete configuration. And for 19, 20, and 21, you're doing the noble gas one. So you're doing the one with the brackets. Okay? So has anybody got a question on doing this worksheet? Because I'm going to put you in your groups here in a sec. Okay, I'm not seeing anything, so I assume we're good. Okay, I'm going to move a few people around and then we'll be ready to go here.